All right, guys. So, because of the roads today, we're not having class. So here's the video that we would, or the lesson that we would do, just doing it on a video instead of in person. So obviously, we're not going to be able to do the cart on a ramp activity today. So we'll pick that back up when we meet again next Monday. So today we're going to kind of cover and review acceleration and uniformly accelerated motion, and we're going to go through some example problems, and we're going to also talk about free fall and examples of free fall. So jumping right in, last time we were dealing with velocity versus time graphs, and we said that the slope on a velocity versus time graph displayed the average acceleration of an object. So again, looking at kind of average acceleration, it's the change in velocity over change in time, or the rate at which velocity changes. So acceleration is a commonly misunderstood concept because people in their everyday lives use acceleration in a different way than what we mean in physics class. So in your everyday life, most time when people say something accelerates, it just speeds up. And in physics, it does deal with like changing velocity, so you could speed up, slow down, or turn when you change velocity. But it also is how quickly that is occurring. So it's a combination of not only the change in velocity or the amount of you change your velocity, either increasing, decreasing, or changing direction, divided by the time. So to try to give you an idea of something that is an example of this, acceleration, again, it's a rate, so time is included. So in this race here, in this GIF, there's several students that are lined up to start a race, and most of the students accelerate at the same rate. So they're all starting at rest, and they start running, and it looks like they stay pretty close to each other. So their velocities are changing in the same amount of time. The unfortunate student in lane 6 here had difficulty with the start. So she took longer to speed up. So her rate of acceleration was less compared to the other students. So she might eventually reach up and get to the same speed as the other students that started the race and were successful with the start, but it just took her longer. Another example of this would be like if you were driving a car and you were at a traffic light, and in the beginning when you start driving in a car, you're probably pretty hesitant, and you barely press on the gas. So you accelerate much slower, so you increase your speed at a much slower rate. So your acceleration is less. So if you're just barely pressing on the gas pedal, you'll speed up and you'll reach whatever speed you're trying to get to. It just takes you longer. Whereas once you are a little more experienced driver, you have gained confidence in your abilities and you just press on the gas to what amount you feel comfortable with, and you accelerate at a larger rate and your velocity increases quicker. So that is what we're talking about. The average acceleration equation, again, it's stated there. Acceleration is measured in meters per second in a direction, or meters per second squared in a direction. So just to kind of talk about meters per second and kind of describe what is happening there. The idea is that, the change in velocity over the change in time. So if we had a change in velocity here, or our velocity values as time goes by, and our time. So if, let's say we're starting out and our velocity initial is 0 and our time is 0. And let's just say we have an acceleration of, we'll say positive 3 meters per second squared. And again, the way that some people understand it better is if they write it as meters per second. So what that means is every second that goes by, so if we go from 0 to 1 second, that's 1 second of time change. That's what's happening here on the bottom. We're going to have the velocity change by positive 3. So if I add up plus 3, that's my change in velocity. I end up at positive 3 meters per second for my velocity. And if I kept going, and the next second I'd go from 1 to 2 seconds, and I'd go from 3 to 6. And we would keep accelerating, and the velocity would keep changing. And eventually maybe we get to, we'll stop at, 4 seconds of time. So that would be for an acceleration of positive 3 meters per second. If we had a larger acceleration, so let's say our new acceleration is something like positive 6 meters per second squared, so obviously that's a bigger acceleration. So it means every second that goes by, it's going to increase by 6. So if we started out for our object here and we started at 0 again for our velocity at time equal to 0, after 1 second it would be 6, and then at 2 seconds it would be 12. So they both reach 12 meters per second, This one, the red object just took 2 seconds, and the black chart or column took 4 seconds. So because this acceleration was bigger, it reached that change in velocity at a higher rate. So again, it's not just changing velocity from 0 to 12. That's not what acceleration is. It's the rate of change. So it's that time measurement is included. That makes a difference. Again, the direction, it just points in the direction of the acceleration, which is the direction of the force that causes the change. So if it was accelerating in the positive direction, if it was horizontal, it would be to the right. If it was vertically, it would be up. So let's talk about how acceleration works in terms of how it causes speeds to increase or decrease. So if the sign of velocity and acceleration are in the same direction, then the speed of the particle or the velocity of the particle would get bigger. So something would go faster. If they are in opposite directions, then the speed decreases. This makes sense. So if you imagine this is me, and I'm going to walk to the right across the classroom. So I have a positive velocity vector. And you wanted to make me change my velocity. So in order to make me change my velocity, you would give me a push. So you'd push in, kind of one direction or another direction. So you could apply a force or push me forward or backward or to the right or to the left. And the direction in which you push apply that force, that is also the direction of the acceleration. So if you understand like what would happen to me if you pushed me in certain directions, that's what's going to happen to the speed. So you'd speed up, slow down. So if we had a car instead of me, or if I'm moving to the right and you want and I want to increase velocity, which way would you push? So if I was moving to the right, you wanted me to go faster, you'd push me to the right. So I have a positive velocity vector and a positive acceleration. So they would agree and the particle would speed up. If I was going to the left, so this time I have a negative velocity, and if you wanted me to speed up, so if this time I'm going to the left with a negative velocity, and you wanted me to speed up, you would push me that same direction. So this would be a negative acceleration. Then some other cases, so those are the speeding up ones. Decreasing velocity, if I'm moving to the left, I have a negative velocity because directed to the left is negative. And then decreasing velocity, if I was moving left, you want me to slow down, you'd push me the opposite way, so that would be a positive acceleration. And then finally, if I was moving to the right, I have a positive velocity, and if you wanted me to slow down, I'd need a negative acceleration. So again, the sign of the acceleration, whether it's positive or negative, that does not tell you whether it speeds up or slow down. It only indicates the direction. This agreement and disagreement, so if they point the same direction or opposite directions, that's what determines whether something accelerates or speeds up or slows down, or how the velocity changes. So we talked about average acceleration, the calculus version. We're getting into the calculus part is determining the instantaneous acceleration, or the acceleration at exactly one moment. So sort of if you just kind of took smaller and smaller time intervals for the average acceleration, eventually you would get to the instantaneous acceleration, which is just the derivative. So similar to what we did with a position time graph, we took or a function of position as a function of time, we took a derivative to get the instantaneous velocity. We do the same type of idea for acceleration, so we just take the derivative of the velocity function with respect to time. It is also the second derivative, which is this notation, which you guys should be familiar with. It's the second derivative of the position function with respect to time. So it's just another derivative. It's not that big a deal. So let's just go ahead and practice a little bit working with this velocity function where it's describing the velocity as a function of time. So it has 20. You don't have to really worry about the units again. So if you want to just ignore that, and when you're doing your calculus, it's 20t minus 5t squared. That's the function that you got. So 20t minus 5t squared. That's what v of t is. And you're going to do several things here. So you're going to find the acceleration. So you're going to have to figure out to take a derivative. Then you're going to find the instantaneous velocity at these times. So you can actually do that now. Just plug in those values here. You're going to find the instantaneous acceleration at these times. So once you take the derivative, you're going to plug in 1, 2, 3, and 5 and evaluate it at those times. And then we're going to talk about what's happening to the motion with those concepts. So whether they agree or disagree in terms of positive and negative, and that would be increasing velocity or decreasing velocity. Okay, so and then we're going to sketch it and kind of look at the graph and see how the graphs match up. All right, so let me pause and give you a second. Like, you should pause the video here and try to work through this problem, and then I'll come back, press play, and I'll be describing what to do. So hopefully you pause the video. If you take the acceleration, it's the derivative with respect to time. So this is 20t to the first power, so it's just going to be 20 because the t is to the first. And then for the second term, you bring the 2 down in front, so it's 2 times 5 is 10. And then you subtract 1 from the exponent, so it's just t. So that is the acceleration function with respect to time. So plugging in 1, 2, 3, and 5 into here, you'll get these values. So you get 15, 20, 15, and negative 25 is the last one. So if you evaluate those properly, that's what you should get. If you plug in 1, 2, 3, and 5 here for these values, you get 10, and then 0, and then negative 10, and negative 30. All right, so if we look at the signs here, these are both positive. So this would be an increase in velocity. Hold on a second. But yeah, this is an increase in velocity because the signs agree. This is a positive velocity and 0 acceleration, so it's really not increasing or decreasing. It's constant at that one instant. It's not changing. Now we have a positive velocity and a negative acceleration, so that would be a decrease in the velocity of the object. And then finally, negative and negative, they agree, so that's going to be an increase in velocity, and it's moving in the negative direction. So that's kind of what's going on here. If you check that out on a graph, if you graph them, here is what it looks like on graphs. So in the first part, you have a velocity that's increasing up until the second where there is no acceleration, so that's the slope of the line at that point is a horizontal. This is a positive slope. Then on the way back down, it starts speeding up, or I'm sorry, it's the velocity slowing down until it momentarily stops, and then it would continue in the negative direction, and it would be increasing in that negative with a negative velocity. So that's those values, and then our acceleration as a function of time is given here. So the acceleration starts out positive. At 2 seconds, it's 0, and then after 2 seconds, it's a negative acceleration. All right. So again, just kind of working through the calculus aspect, doing a derivative, plugging in and evaluating, and doing all those things. All right. So the main part of today's lesson is talking about motion with constant acceleration. So lots of times, acceleration is constant or fairly close to constant that we can approximate it. So we develop a whole type of method to solve problems that have constant acceleration. So there are 5 equations that we can use, and the constant acceleration means that a velocity with a constant slope and a position with a varying slope. So these are what the graphs look like if you have constant acceleration. So you'd have some sort of curve or quadratic function here for position. You're going to have a velocity that is linear, and then the acceleration would be linear and horizontal, so there would be no slope on that acceleration. Okay, so so those are your possibilities with graphs. So the way that these equations work, here are the equations. I think you watched another video with Flippin' Physics where he took you through these equations and derived them, or talked about how to use them. Again, I use slightly different notation, so instead of having 2 different letters here like x minus xo, I just call that like change in x. That's really the only difference there, so I just group those together anywhere they're at. These 5 equations are used to solve for whatever quantity might be missing. The steps that I use in solving the problems, the first thing I do is always draw a picture. Then I'm going to identify the givens in a table. So I make a table that looks sort of like a horizontal table like this, where I list out the 5 variables: delta x for the change in position, the original velocity VO, VA for the acceleration, and T for the time. So I plug in for those variables. I identify 3 out of the 5. So I need 3 out of the 5, identify what I'm looking for, which is the question mark I put in my chart. And then the box that is not filled in, it doesn't have a number and it doesn't have a question mark, that is the missing quantity. It is much easier to identify the missing quantity and then the equation to use based on that missing quantity, rather than trying to verify that the 4 things that you know about, the 3 numbers and the question mark, are in that equation. So I'll demonstrate this in a second, but I think that's an easier way to go about it. You plug in and do algebra, and then you keep going and check to make sure it's reasonable. These equations only work if the acceleration is constant. So if you have a non-constant acceleration, it will not work. These equations also right now are written for horizontal motion, but there's just a couple small changes to get to vertical motion or free fall, which we'll do in a few minutes. So just to test whether you know whether or not the uniformly accelerated motion equations apply, we have 4 different functions, position as a function of time, 1, 2, 3, and 4. And you're going to have to decide which ones apply to the uniform accelerated motion equation. So let me pause and give you a second to consider that. So if it's uniform accelerated motion, we want the acceleration to be constant. So when you solve for the acceleration function with respect to time, it should be a constant value. So if you do this one, so again, to get to the acceleration, you have to take the derivative twice. So the first derivative will get you the velocity, the second derivative will get you the acceleration. So if you take a derivative here for the first one, 3t, the derivative of that would just be 3, derivative of -4 is 0, and then if you take a derivative of 3, you get 0 for the acceleration. So yes, that one works because 0 is a constant value, it's a number. If you do this kind of thing, if you look at the order of the operations, if you end up with t at the end, it's not going to work. So for the velocity, this would be like -15t squared. This is going to be 8t. 6 goes to 0. And then you take the derivative one more time, and this is going to be 2 times -15, which is a -30t, plus 8. This is non-constant because t is a variable that changes. So if you put in time 0, time 1, time 2, you're going to get different values for a. So this one is not good for the uniform acceleration motion or uniformly accelerated motion questions. This one looks a little weird, but you just have to rewrite it. So it would be 2 times t to the -2nd, and then minus 4t to the -1, and then it's just the power rule again. So this is not going to end up being constant as well, because this is going to go to the -4th, and this would go to the -3rd. So again, the time is a variable in the acceleration one, so that's not constant. If we do this one, though, it does work out. So velocity would be 10t, and then the acceleration would just be 10. 3 is going to go away in the first derivative. So yeah, 4 and 1 are the 2 functions that with respect to time that will work. So if it's more than x equals some variable or some constant with t squared is the biggest one that you can have, the biggest exponent you can have, and make it work out so that it follows uniform accelerated motion equations. All right, so let's try a problem. So the first question here says drag racers can achieve an average acceleration of 26 meters per second. If it's average, it's not changing, so that's going to be constant. Suppose dragsters accelerate from rest at this rate for 5.5 seconds. How far does it travel? And then what's the velocity at 5.56? So for your picture, you can draw a car if you want. So there's my dragster. You don't have to make it, as beautiful as my picture here. You can just write a dot. I'm going to write, it says it starts from rest. So rest is an important concept. So I'm going to write that down. And then I usually draw a couple arrows just to show what the thing is doing. So once it starts moving, it's going to accelerate and go faster in terms of the description here. So that's a good enough picture. So that's fine for the drawing. For the table, I'll write it out a little bigger because I realized that was pretty small the first time. So I usually write delta x for the change in position. VO is the original or initial velocity. V is just the velocity at some time later. A is our acceleration, that's constant, and then time or change in time is the value for the last term. So reading through this, average acceleration, so 26 is going to go in this box. If you want to write the units, you can. I'm not going to worry about it. starts from rest. So if it starts from rest, the initial velocity is 0. And then it travels for 5.56 seconds. So right now we have 3 numbers out of the 5. So we are good to start trying to approach and solve this problem. We have enough information that we can solve. Part A asks for how far does it travel. So how far is not the final velocity or velocity later on. It's going to be the displacement. So I'm going to put a question mark in there and write A because that's what we're looking for part A. So the missing box is this one, this velocity. So we're going to go back to those equations and we're going to find the equation that doesn't have this final velocity, which would be that second one. So I'm going to use that equation. It is much easier to just identify what's missing and then use the equation that doesn't have it, rather than to try to check for 4 things, because each of these equations has 4 things. So it's much easier to do this. So it is this formula here is delta x for part A. Delta x equals v naught t, or delta t, plus 1/2 a, and then it's t squared. You just plug into this. It's not overly complicated at this point. It's just plugging it into a mass. So the initial velocity is 0, so that whole first term is going to go away. Delta x is what we're solving for. So it's 1/2. The acceleration is 26. And 5.56 is our time value. And make sure you square it. When you're doing these problems, when I check this on like your tests, I expect you to do this level of work. So again, for drawing a picture, you get credit. For filling out the table, you get credit. For writing out the equation that you intend to use, you get credit because that is showing me that you understand the physics in the problems. Plugging in, solving, getting a value, the number at the end. When I did it here, I got 402 meters. It's not exactly 402, but it's close. It's like 401 point something. That is the kind of concept. But again, you get credit all along the way. If you don't do these steps, you don't get credit for it. So please, please, please show all your work. Part B wants to know what's the final velocity. We can put this 402 in here if we wanted to for our answer here. Once you have 4 out of the 5, so now we have 4 numeric values, we're looking for the final velocity. You can use any equation you like. I usually tell my students to pick the easiest one. The easiest one for this setup is V equals VO plus AT. And again, it's just plugging in and evaluating the numbers. So V is what we're looking for. VO is 0, so that's going to go away because we start from rest. So it'd just be 26 times 5.56. So if you happen to multiply those out, you would get 144.6, and it's meters per second. Just be careful reading the question and make sure you understand conceptually what's going on. That's where the picture helps. Some of the problems are more complicated than this one. So you want to make sure that you're doing and putting values in correctly. Be careful with signs. So our acceleration and our velocity agreed. They're both going to the right. It didn't say it was going to the right, but I just drew it that way, and I made it a positive acceleration, so we ended up with a positive velocity too, because we started from rest. All right, so that's the first one. The second problem, a car traveling at 30 meters per second on a highway. The driver sees the traffic light change from red to green and takes 0.5 seconds to begin braking. So there's like reaction time in this one. They apply a constant acceleration of a car as 7 meters per second squared. How far away from the traffic light does the car need to begin braking so that the driver doesn't enter the intersection? And then what is the time that the car needs to stop? And I might have skipped that part, but I'll go back and do it together. So but I was just looking at my work. So I'm just going to draw a dot for the car this time. So there's the dot. And I have the car moving to the right at a constant 30 meters per second. So if it's a constant velocity, our arrow, I'm going to change colors for the arrow, our velocity arrow should be the same length every time. So this arrow and that arrow should be the same length. And I'll just put that as section 1. And that's the reaction time part. So that's when the car is just driving along at a constant velocity. Then after that, the car starts to brake. And when you brake, you slow down. So I'm going to make the arrows get smaller. Okay. Eventually, the car is going to stop. So I'm going to put a arrow there too, and write stop. And I'm going to just say this is section 2. So we have 2 different sections. In the first section, the motion of the car is using a constant acceleration. It's just the acceleration 0. And in this one, the acceleration is equal to, according to the problem, it's 7. If I write 7 here, 7 meters per second squared, does that make sense the way that it's written? So this is positive. If it was positive 7, it would speed up. So you're going to have to put in that negative. So be careful with that. This is where I said, make sure you're understanding the situation and reading the problem. So you could really do 2 charts. You don't really need to with the part 1 because part 1 is really basic. It's just a constant velocity. So the displacement is just the velocity times the time. So we can do this right away. So the velocity is 30, and it's going for 0.5 seconds before they start braking. So 30 times 0.5 is 15. So we have 15 meters traveled before the car starts to slow down, and that's for part 1. So I'll just write a 1 there. All right, for part 2, this is where we're going to need our acceleration values and our chart. So we're going to plug in for this. So we're going to look for delta x here. The velocity initial, velocity final, or later on, acceleration, and then time. So, so delta x we are looking for, because we're looking for how far does it travel. We need the whole distance, so we're going to want to calculate the distance for this section plus the distance for section 2 when it was slowing down the stops, and we're going to add those together. So coming back to here, the initial velocity when it enters the second section, or when it begins to brake, is 30. Eventually it's going to stop, so that's 0, and then our acceleration is -7. So we're going to go ahead and use an equation that doesn't have time, because that's the thing that's missing. So the equation without time, if you go back and look, is this one. So it's v squared equals v naught squared, or original velocity squared, plus 2 times a times delta x. So when you plug into this, 0 squared is just 0, 30 squared plus 2 times -7 times delta x. So 0 squared, again, like I said, is 0. 30 squared is 900 plus 2 times -7 is -14, and then delta x. We got to do some algebra here and solve, so I'm going to take this -14 to the other side and make it becomes positive. So 14 delta x equals 900. And then you divide through by 14 to solve for delta x. So again, just going through all the algebra here, showing the work. For delta x for part 2, it turns out to be 64.3 meters. So we're going to add the 2 sections together, and delta x total for the whole time when it's traveling for reacting and then braking is, if you add 15 and 64.3, it's 79.3. So 79.3 meters is the total amount of space that the car needs to slow down and stop. Part B, I'm just going to do really quickly right here. So part B wants to know what is the total time the car needs to stop. So we already know it's 0.5 seconds for the first part, so we just have to solve for the time here and then add the 2 times together. So I'm going to use the equation V equals V naught plus AT. That is the easiest equation, in my opinion, to use to solve for the time. So the final velocity is 0, the initial velocity was 30, and then the acceleration is -7t. Similarly, solving, you take the 7t to this side equals 30, and then divide through by 7. You get the time for part 2 to be 30 divided by 7, which is 4.28. I'll just say 4.3. So that's the time for 2, and then we want to add the time for 1, which was 0.5. So the total time is 4.8 seconds. So again, similar kind of concept. This time we're figuring out times instead of displacements, but it's same kind of idea. All right, so hopefully that's doing pretty well. We're getting into the last topic, which is getting into free fall. So let's talk about that. All right, so free fall is a topic, but basically just kind of the same type of motion. So it's constantly accelerated motion or uniformly accelerated motion. It's just in the vertical direction, so it's up and down instead of horizontal. And the defining kind of factor of free fall to make it free fall is vertical motion, where the object is only affected by the force of gravity. So the force of gravity is the only force that is contributing to changing the motion. So that's the only force that's accelerating the object. All our other forces can be ignored, so we don't worry about air resistance or thrust or any other type of force that could cause a change in the acceleration. So one thing that we need to just kind of briefly discuss is the force of gravity versus the acceleration due to gravity. So those are two different things. The force of gravity is the pull of the Earth on a mass. So it's the attraction between masses, and what we commonly refer to the force of gravity on Earth is the weight of an object. So your weight is describing the force or the pull of the Earth acting on the mass of the Earth, attracting the mass of the object. The acceleration due to gravity is a different concept. So the acceleration due to gravity is the rate at which gravity changes, the force of gravity changes the motion of an object. So the force of gravity is the weight, and the acceleration due to gravity is that idea of acceleration. So we use a symbol for the acceleration due to gravity called little g. All right, so that's the acceleration due to gravity. The force of gravity I usually write as capital F G. And when you're close to the surface of the Earth, it's just little m, little g. So you're going to take the mass times the acceleration due to gravity. So they're pretty similar, but they're not the same thing. All right, so one thing we need to know also is these equations only work during free fall. So free fall is when the force of gravity is the only force acting. So it's important to be able to identify when free fall starts and when free fall ends. So I have a couple GIFs here to kind of discuss. So we have Ariana Grande, I believe, dropping a microphone. And we want to talk about when is the microphone in free fall. So I can't pause it, but when does free fall start? It starts when it leaves her hand. So while she's holding the microphone, it is not free fall because there's another force acting. So as soon as she lets go of the microphone, that's when free fall begins. It's falling, and when would free fall end? When that microphone hit the floor. So between releasing it and when it hits the floor, that's free fall. That is the only part we can describe using these equations and formulas that we're going to learn. This person is juggling over here, so they're throwing a ball upward, or several balls upward. The free fall in this situation begins when, again, it leaves his hand. So if he's not pushing on it anymore, that's when free fall starts. And free fall ends when it touches or there's another force acting. So when it goes to his other hand and he catches it, that would be the end of free fall. So it's really important that you don't consider like free fall situations to like after something has another force applied. Okay. So just to kind of talk through a situation to demonstrate what's going on in free fall and considering how the acceleration due to gravity changes the motion of an object. Let's talk about this situation. So again, acceleration due to gravity near the Earth we assume is a constant, and we're going to say it's negative 9.8 meters per second squared. The negative sign indicates the direction in which it's going, so that's always towards the center of the Earth, which in our frame of reference is down. So let's say we take a situation where I throw this ball upward at positive 30 meters per second. All right, and I want you to think about what's going to happen to that velocity as the ball rises and as the ball falls. Just a note, I showed the ball moving horizontally across. I'm just throwing it vertically upward, but in order for the balls not to overlap, I had it kind of move to the right so we could tell. So generally, let me ask you a question. What do you think is happening as the ball rises? So what's going to happen to this velocity of 30? How's it going to change when it gets to this position or this position or this position? So again, it's important to kind of describe gravity. Gravity is always negative 9.8 meters per second squared on Earth. So if I have a positive velocity, which is going upward, and I have a negative acceleration due to gravity, which is downward, they're disagreeing with each other. They are going in opposite ways. So as it increases, or as the ball moves up, as it rises, velocity decreases. That's what should be happening as the ball rises. And then on the way back down, as it falls, the velocity is going to increase because you have a negative direction for the velocity. So I have a negative velocity going this way, and I have a negative acceleration, so they're going to increase. So if I draw these arrows kind of going up, the arrow is getting smaller on the way up until it reaches the highest point. The highest point I call the apex. And at the apex, that is where the ball changes direction. So it's going from a positive direction to a negative direction. And at the apex, the velocity is equal to 0. So at that moment, at the apex, the velocity of the object in free fall is at its highest point. It's at 0. On the way back down, the arrow is going to get bigger. It's going to increase until it returns back to that same amount. Just kind of tracking it, if we set up a table. So if we track velocity as a function of time. So we're throwing at 30 meters per second, and this is at 0 seconds is when it leaves my hand. Let's just approximate gravity to be -10 because that will be easier to track. It's not exactly that, but it's close enough that we can estimate it. After 1 second, what's this velocity? So how fast is it moving if this is 1 second into the motion and this is 0 seconds? I would say that if we take away 10, it's going to be 20 meters per second. So it's going at 20 now. All right, 20 meters per second up. In another second, 2 seconds here, it would be 10 because we're using this -10 meters per second. So every second that goes by, every time we add a second, we're going to add a -10. So add a -10. We add another -10, that's going to get us to 0, and that's at 3 seconds. So this is the apex. So our apex occurs when the velocity equals 0. And that's about 3 seconds in time. And then if we keep going at 4 seconds, it's going to be going -10, approximately 5 seconds, -20. And then 6 seconds, it'd be back at -30. So if we look at this kind of motion and this description of what's going on, this looks very symmetrical. So 4 seconds, 5 seconds, 6 seconds. So it took the same amount of time to rise as it did to fall. If you check the velocities, they have the same velocities at those different instances. They're at the same positions on the way up and the way down, and those kind of instances as well. So this is very symmetric. It's a parabola in its nature. Okay, so the uniform accelerated motion equations are exactly the same for free fall, but x is just replaced by y, and a is replaced by g, which is always on Earth, -9.8 meters per second. So I just replaced them here, so I just copied this down. So this is the equations we had in the beginning. All you're doing is replacing x's with y's and a's with g's, and you can see that kind of there. The problem-solving strategies are the same as well. So you draw a picture, you set up your table, you figure out your values that you figure out what your unknown is, you figure out what equation is missing so you can determine the right equation to use, or what quantity is missing so you pick the right equation, and then you go ahead and do the algebra and solve. So we're going to finish up by doing maybe 2 more problems, and then this will be the end of the video. Sorry it's a little long. It's not longer than my normal, but it's the lesson for today. So free fall problem number 1, a ball is thrown downward from the top of a 98 meter tall building with initial velocity of 4.9 meters per second. So we got some numbers, so I'll know those. It says how long does it take for the ball to hit the ground, and then with what velocity does the ball strike the ground. So I want to say probably free fall problems are a little more tricky, or you need to just be more aware of positives and negatives in these types of problems. A lot of times people make mistakes in these, so be careful. So our problem, we have some velocity downward. It's going to go faster on the way down, so I'm just going to make my second arrow bigger. That's a good enough picture. And then we need to set up our table. So for our table, we got change in position, which is now the y direction. VO, V, G, and delta t. If you want to get in the habit of writing little y subscripts here, vy and voy, you can do that if it makes you feel better. Eventually, next lesson, when we get into projectile motion, you're going to have to start determining whether it's an x or a y velocity when we do components. So anyway, if you wanted to do that, you could. So again, you have to establish where things are. So I'm going to say this is 98 meters up because it's above the ground, which I would call the ground 0 meters. So that's fine. I'm gonna do that, and then I'm gonna plug in the numbers. So 98 meters is where the ball starts, and it moves down to 0. So I'm gonna say it loses 98 meters of height. It's decreasing its height by 98 meters. That's what that is. Be careful. That's probably the first sign mistake that you might make. The initial velocity is 4.9. Which way is it being thrown? 4.9 meters per second. It's being thrown downward. So again, you have to put in this negative sign if it is not explicit and tell you that. Gravity is always negative. It's always downward. It's negative 9.8 meters per second squared. So there were only 2 numbers in the problem, but because we know gravity, we have 3 out of the 5. So again, once you have 3 out of the 5, you're good to solve. Part A, how long does it take? So we're going to solve for t. That's for part A. For part B, it wants to know how fast it's moving, or what's the velocity, how fast and the direction, and part B. So those are the 2 things that we're going to solve for. One thing I also want to mention here is that you don't have to do the problem in the order that it's described. Sometimes it's helpful. Other times it might be easier to do part B before part A. It's up to you. This one is one where it's a little trickier if you do part A first, but I'll show you how to do it. You guys are smart and you can do it, do the math, so you'll be fine. So if I'm using the equation without Vy, it's this one. So it's delta y for part A. Delta y equals VO t plus 1/2 a t squared. So delta y is negative 98. VO is negative 4.9 t plus 1/2 times negative 9.8 t squared. So what we have here is we have a quadratic type expression. So if I simplify this, it's negative 98 equals negative 4.9 t, and then I have plus half of negative 9.8 is a negative 4.9 again, t squared. So I have a quadratic function, and most people, like I don't particularly like solving quadratic functions, especially if they're not factorable. This one actually is factorable, so I'll show you how to do it with that. But you could use the quadratic expression here, quadratic equation, and solve that way as well. So I'm going to divide everything by negative 4.9 because that's a factor that I can take out. And then it becomes a little more obvious as to what the right way to go about this is. So if I divide that out, it's going to be 20 equals negative t, positive t plus t squared. So I'm going to bring the 20 over to this side, so I have 0 equals, and then regroup the order, so t squared plus t minus 20. And hopefully you recognize, oh, that's pretty nice and easy to factor, so I'm just going to factor it out. So the 2 numbers that would work out to get me negative 20, where the difference between them is only a positive 1, it'd be a positive 5 and a negative 4. So if you check that, that works out mathematically. And then you just have to set each one of these equal to 0 individually and solve. So t could be either equals negative 5 seconds or 4 seconds. So one of those makes sense and one does not. We can't have negative times, so this is not correct. And 4 seconds is the right answer. So you could definitely do it that way. We just did it using that. You could use the quadratic formula, so you could have done that. You could have also solved for part B first and used an equation that didn't have time in it, and then go back and solve for time. Either way, it works out. Let's go ahead and solve for part B. So it wants to know the final velocity, so I'm going to just solve for V. V equals VO plus GT. I'm going to use the time that I just got in my answer, so that's fine, and I want to use the 4, not the negative 5. So V is what I'm solving for, negative 4.9, and then it's going to be plus negative 9.8 times 4. So when we put that in the calculator, you'll get negative 44.1 meters per second. It is negative, which means it's moving downward, which makes absolute sense because that's the way it should be, the direction it should be traveling when it does that. You, again, could have done this in a different order. You could have done B first and A first. If you want to practice that, you can. I try to avoid quadratics unless I can just tell it's factorable, and this one was nice and did that. But you can avoid that if you wanted to do B before A. All right, one more problem here. So this one has several parts to it, so it's kind of testing you conceptually, and this is the last one for today. So it says a batter hits a baseball straight upward at home plate. So the baseball is hit upward. And the ball is caught 5 seconds after it is struck. We're going to assume that the ball is hit and caught at the same location and same height. So as it rises, it goes up, it's slowing down, it gets to the highest point, or the apex, which we describe it as, and then it's going to fall back down and be caught, and it's returning to the same level. Part A, we want to know the initial velocity of the ball, so how fast is it hit going up. B, what is the maximum height the ball reaches. C, how long does it take to reach the maximum height. D, what is the acceleration of the ball at the top of its path. E, what's the velocity of the ball when it's caught. And we're going to assume, again, that the ball is hit and caught at the same location. So I'm going to start trying to fill in my chart. With these, in this particular problem, using the apex is helpful because you might not know enough information if you don't use that position. So delta y, we're not sure about. The initial velocity, we're not sure about. If we use the apex, I'm going to write apex above the velocity here so I know that's where I'm talking about. The apex, the velocity is 0, so that's good. Gravity, we know, is negative 9.8. And then for the time, it tells us the time, but it tells us the total time. So the time it starts at, it would be 0 seconds. Time that it returns is 5 seconds, and it's caught at the same level. So hopefully you guys remember the time up and the time down are the same. So if this is 0 and this is 5, 2.5 seconds would be the time at the apex, and I'll call that the time up. So the time going up is 2.5. So I actually do have 3 out of the 5 that I can solve for. We also answered, this is part C, how long does it take to reach the maximum height? So 3.5 seconds up, so it's just half of the total time. We want to know the initial velocity, so that's my question mark. So I want the equation without delta y. So for part A, v equals v naught plus gt. The initial velocity is not 0, that's what we're looking for. Sorry, the final velocity, or the velocity at the highest point, that's 0. VO is what we're looking for, and then I have negative 9.8 times 2.5. So if I solve that out, I get VO is equal to, it is 24.5 meters per second. Now, is the ball going up or down? It's going up, so that's why the positive value makes sense. So that's part A. Part B wants to know how far it travels upward, so we're looking for delta y. You can use any equation that has delta y in it at this point. So the one that I think is the easiest to use is this one with the half. So 1/2 VO plus V, that quantity times the time. So delta y is 1/2 the 24.5 we just got for the initial. The final velocity, or the velocity at the highest point, that's 0. And then the time going up is still 2.5 seconds. So if I multiply all that out, I get delta y is equal to 30.625 meters. We've already said C, the answer is 2.5 seconds because it's the time up, which is equal to half of the total. So we did that already. D, what's the acceleration at the top of the path? Acceleration is equal to What in free fall is equal to gravity? It's kind of a trick question. This question gets asked a lot. It will probably get asked on your test, so make sure that you pay attention to questions that ask about the accelerations in free fall. There, if it's on the Earth, it's negative 9.8 meters per second squared. E, what's the velocity of the ball when it's caught? You could do this equation for 5 seconds with the initial velocity. It turns out that it's the same. So again, it's 24.5, but this time meters per second, it's traveling back downward. Again, that's the symmetry bit. If it's thrown up and returns to the same level, it's got the same initial velocity and final velocity in magnitude, but they're in opposite directions. So that is your final velocity there. So that is the lesson for today. Sorry guys, it's a little long, but I wanted to make sure I got through everything that we would talk about. So so you're gonna do the watch this video, which you've done, velocity versus time graph practice, and then I would say start homework number 2. Homework number 2 you should be able to get started after this lesson, and spend some time on it today, and you won't have to stress. It's kind of long, so there's like I think 15 questions. It's longer than the first one, so it's going to take you a little bit more time. So anyway, hopefully this lesson goes okay, and I will see you guys next Monday. Be well.